So, welcome to an invited talk at the section on dynamical systems of the ICM. And it's my great pleasure to introduce the speaker for this afternoon. That's Professor Michela Procesi. Let me just sort of say a few words about her. She got her PhD in 2002 at Sapienza, and she spent sort of postdocs at various places, but finally she became a full professor at Roma III. Her work is on COM theory, NLS, and similar kind of topics. And she also received an ERC grant, which is called Hamiltonian, with the title Hamiltonian PDEs and Small Divisor Problem. So I guess the talk today will be sort of somewhat in this direction, but the official title is Stability and Recursive Solutions of Hamiltonian PDEs. Michela, please.
So thank you very much. Well, of course, I'm greatly honored to be given the opportunity to speak. Also slightly terrified by the setup, but okay. And very glad that I can do it live. So thank you all for staying here. So, can I speak? Well, hopefully, since nobody is saying anything, everything is fine. So what I'm going to talk about is setting of infinite dimensional dynamical system. And especially, I want to discuss some special classes of solutions which appear in the modeling of waves. This is not working. Okay, should I do it there? No. So, well, using nonlinear PDEs to model wave is a very reasonable paradigm. There are many very famous examples. What I like to think about is the setting of hydrodynamics, because everybody can imagine a wave profile. And so it's nice. And there are lots of examples which are more realistic. So Euler equation, Navier-Stokes equation. But what I like to do is to stick to simple models. So models which represent the behavior of a wave in some certain regime. And then try to understand the still very rich behavior, which comes from the fact that it's a nonlinear dynamical system in infinite dimension. So I wrote some examples. Let's try the pointer. First one is nonlinear Schrödinger equation. The second is Korteweg-de Vries equation. Last one, a bit more exotic, at least for me, Kamasa-Holm equation. So these are all equations that come out from modeling water waves. And what is the idea? So here, I'm sorry, this should be U. The idea is that this U describes the interface, so the profile of the wave. And why is this one-dimensional? So this is X, which lives in R. Well, because you think of a plane wave and just make a section, and then you get a reasonably good model. I forgot to start the clock. Okay, well, I'll look there. So these are very nice models. They have been studied in lots of contexts. And but really what you should know is that they are all integrable PDEs. And while there is a vast literature on integrable PDEs with many extremely interesting results, the things that I'm going to talk about do not depend on the integrability. So these are just nice equations that I wanted to write, but you could change them. So there are, well, safer and less safe ways of changing the equation. The safest way is that you add a small perturbation. So you add a piece here with some epsilon in front. And actually, since I'm going to look really just at small solutions, so U would be small in amplitude, if I add here a piece which is an analytic function of minimal degree 5, then it's a small perturbation automatically. And you could do the game with all these equations. But in fact, provided that you are careful a little bit, you could completely change the nonlinearity. The thing that you have to be careful and you should notice is that here in the nonlinearity, I don't have any derivatives. While in these, you see, I start having derivatives. And in this last case, I have as many derivatives in the nonlinear piece as in the linear term here. Okay, so this will make results more and more complicated, and you should watch for that. So apart from that, and trying to avoid some too pathological cases, think of any nonlinearity. Then, of course, maybe you want to go to higher dimension because the plane wave are not the only waves that exist in the world. And once you decide that you're higher dimension, you can think that you're working in Rn. And then, so this is an example of a nonlinear Schrödinger equation. And you might want to ignore this P, just think mod U squared times U. So this might be an equation given on a domain on Rn. Possibly it should be a simple domain with a simple boundary, very smooth, because these things are rather difficult to deal with. Or it might be a Riemannian manifold, and then this delta here will be the Laplace-Beltrami operator. Well, since I want to look at the phenomena of propagation of waves, what I'm going to do, I'm going to consider mostly PDEs defined on compact manifolds, and actually compact manifolds without boundary. Why? Because if I'm in an unbounded domain, I could imagine that whatever phenomenon should be localized and then at some point escape to infinity. While if I'm in a bounded domain, I expect to see a much more like a recurrent behavior, and it's more interesting from my point of view, except that this is rather hard to do. So I'm going to stick to tori. And for me, a torus is just, okay, Rn mod 2 pi z to the n, which means basically that for all my purposes, these functions u are periodic in each of the x variables and nothing more fancy. And then, what I have to, so let me remember what I said. I said these equations are not integrable, they're nonlinear. So what you should expect is probably there is a lot of chaos going on and lots of very complicated behavior. And on the other hand, all the equations that I wrote have a Hamiltonian, or maybe they might have a reversible structure. So they have some symmetries. And in that case, at least in finite dimensional analogs, you know that there should be coexistence of regular and chaotic behavior. And in some sense, you have to choose. So which kind of behavior I want to look at. So I chose the regular behavior. So I'm going to consider a PDE on a torus Tn, and I'm also going to consider it close to an elliptic fixed point, and I hope to convince you why. Then I'm going to study the existence and stability of very special invariant manifolds, so they're invariant tori, of dimension which has nothing to do with the starting n. I will call it D. And also I will take a dynamical system point of view. So dynamical system point of view here is an extremely naive slide. I'm ashamed of myself. So just think of a first order ODE in an infinite dimensional vector space, u dot equal f of u. And well, if you even want to try to fit a PDE in this context, your vector space should be a scale of Hilbert spaces. And, or maybe scale of Banach spaces, you don't really need the Hilbert structure. And then f should be some nonlinear functional from V to itself and maybe smooth or with some regularity. So let's try our example. My favorite example is always the NLS, so be warned. Take the cubic NLS on Tn. So what I'm going to do is I'm going to pass to Fourier coefficients, because then I will have an infinite dimensional dynamical system on a sequence space, which I like a lot. So what I'm taking as phase space is the union of the Sobolev spaces. So I take my function of x, I remember that's 2 pi periodic in each variable, I write it in Fourier. So it's the Fourier indexes are in z to the n. And then, so what does it mean that I am in some HP? This will control the regularity. And it's rather well known that regularity of the function implies decay of the Fourier coefficients. So here I'm requiring that the uj decay like j to the minus 2p. And here, this is the Japanese bracket. It's just maximum between 1 and mod j. You can safely ignore it. Then just take this equation, pass to the Fourier coefficient, and you get something that formally looks exactly like the thing that I wanted to discuss. This is f of u. The point is that I'm dramatically cheating because this first piece here actually maps HP into HP minus 2, so it's defined on the scale of Sobolev spaces. Whereas in order for this, which is an infinite sum, to make sense, you actually need that the uj are at least, let's say, in HP with p larger than 0. So there are some well-posedness questions which I'm completely ignoring in favor of giving this examples. So if you go to the more exotic example, well, essentially you fool around with the equation a little bit, and then you get something that looks very much like this. So you have a linear part where the linear eigenvalues are purely imaginary. So I have I times lambda j. This lambda j will not be mod j squared, it will be more complicated. Actually, in this example, it's exactly j, but potentially more complicated. And this p also will be more complicated. The difference coming from the fact that here I have derivatives in the nonlinearity, this is called a quasi-linear equation, is that in fact, whichever regularity I choose for u, so even if I'm in HP with p large, it's never true that this is a map from HP to HP because of the derivatives. So this is the only difference, but formally it's exactly the same thing. So what does this mean? This means that essentially you can consider a model which is u dot equals some nonlinear functional. The linear part will be some unbounded linear operator with pure point and purely imaginary spectrum. And then I have a nonlinearity. Okay, then you pass to the basis of eigenfunctions of L. And then you will get something that at least formally looks like this, provided some basic properties hold. And the fact that here I have purely imaginary comes from the fact, because I asked for it. So what is this? This is an infinite chain of harmonic oscillators coupled by a nonlinearity. And I could play this game not only for tori, but the more complicated manifolds or different equations. The only thing that I really need is some good information on the eigenfunctions of this linear part, because I want to compute this nonlinear part rather explicitly in the basis of the eigenfunctions. So this is not a completely trivial question to deal with. So now, as I said, I want to find invariant tori. So what here, this is very naive. So once I have an infinite dimensional dynamical system, what is an invariant manifold? Well, to have an invariant manifold, I actually don't even need well-posedness, not even local well-posedness. The only thing that I need is that M is an invariant manifold. If I take any initial datum on the manifold, then the solution exists for all times and stays on M. What happens outside of M is completely irrelevant. And well, an invariant torus is an invariant manifold, which is diffeomorphic to a torus. So I have a map from a d-dimensional torus into the phase space, and the image M is invariant. Well, then actually I want to do a little bit more. I want to find an invariant torus, which is the support of a quasi-periodic solution of frequency omega, which means that if I take the equation, so u dot equal f of u, and I pull it back on the d-dimensional torus, this will give me the very simple linear motion. Theta goes into theta plus omega t, which of course means that capital U of theta plus omega t is a solution for all theta and all t. So I get one special global solution for my PDE if I find something like this. Now, this is all very nice, but since we are in infinite dimension, well, I would like also to find infinite dimensional invariant tori. And this becomes rather more tricky because what is an infinite dimensional invariant torus? Okay, for me, it's a diffeomorphism from some infinite product of circles into the phase space. So that if you take the dynamics and you pull it back on this torus, you get the linear dynamics, with the only difference that now omega, the frequency vectors in which this linear dynamic moves, is an infinite vector, okay? And, but of course, well, and I'm using Z as index set just to choose something, anything, any countables that will be fine. So the point is, of course, if I want to do this and this to be a diffeomorphism, I have to say something about the topology. So for me, the nicest one, maybe So there might be some debate, but the one I like best is the one that makes the infinite torus a Banach manifold modeled on L infinity. So what I want is I want to measure the usual distance between two angles and then take the supremum over my index set, which is an infinite list. And this is not the product topology, so different. And then if I want this map to be a diffil, this in some sense forces me to work in a phase space, which is again based on L infinity. So I will not work in a scale of Hilbert spaces, but I will work on a scale of Banach spaces based on L infinity. But apart from that, so you can certainly look for an infinite dimensional invariant torus that looks like that. So since these are, after all, rather complicated things to deal with, what I'm going to do, and I'm mostly going to work in a perturbative setting, which I can sit in two equivalent ways. So first way, I have one approximately invariant torus, and I ask myself, is it true that there is a truly invariant one close by? And the second point of view is, well, assume that your nonlinear vector field is some normal form plus a perturbation. So P should be small in some appropriate norm, while N0 admits at least one invariant torus, but you would really like to have a packet of invariant tori. Okay, so assume that N0, all the dynamics is on invariant tori. Which of them survive when I add the perturbation? And once you've done that, well, you might want to know what happens nearby, because after all, I might be able only to find a few invariant tori, but if I can thicken them and find information on a neighborhood, that might be more interesting. So there are two classes of interesting questions. One is assume that you start close. Do I stay close to the torus and for how long times? So the interest there is to find a lower bound on the stability time. And the other question would be, assume that you have two invariant tori. Can I find a solution that starts close to one and goes close to another? Or assume I have one invariant tori. Can I find a solution that starts close to one and goes to infinity? And of course, the first thing that you should do in an equation like this, remember that this has a zero at degree at least 2, is to start with 0. So what happens so 0 is certainly an invariant torus, maybe a bit simple. And what is the stability and instability issues of this torus? Well, there is a world of literature. And I wrote some names for stability, some names for instabilities. All these names actually worked on the nonlinear Schrödinger equation, because otherwise the literature would have become really, really vast. And the interesting thing is that always remember, we are in an infinite dimensional setting. So when I say that I'm close to a torus, I have to say in which topology. And this becomes really an important point. So am I close in a very strong topology, then what happens to the stability times? It's very different classes of phenomena. And of course, again, you could ask this question for equations which are not on compact domains. And there's, again, a body of literature on that, except that it's very different. So not even going to go there, just wanted to mention it. So what I'm going to do is, instead of looking at u equal to 0, I'm going to look at u small. So I have my chain of harmonic oscillators plus a perturbation. And if I ignore P, I can solve everything. And what do I get? I get uncoupled harmonic oscillators with linear frequencies, lambda j, and they just rotate, as one should expect. So all the solutions are on invariant tori, which was my model normal form with invariant tori plus perturbation. And the dimension of this tori depends on two things. One is how many of the initial datum are different from 0. So if uj, you see this is a rotation, and then I have a superposition of these rotations. And if one of the uj0 is 0, it just doesn't count. So usually instead of writing it in this form, you want to stress which are the non-zero solutions, initial data, by writing it as square root of xj. Just remember, because it's a notation that I will use. And you ask yourself, which solutions of the linear systems survive the nonlinearity? And if you ask a question like this in infinite dimension, first thing that you should do is look at finite dimension. So in finite dimension, the point is Km theory. And Km theory gives you a rather strong result because it says, so imagine that this is finite n number of oscillators. It says that under some non-degeneracy assumptions, either on the linear frequencies, or if you can't move the linear frequencies on the non-linearity, then majority of initial data live on quasi-periodic, live on invariant tori, and they give rise to quasi-periodic solutions. And then, so this Km theorem results, it's essentially a quadratic algorithm which selects which linear solutions survive when you add the nonlinearity. And the point is that you find obstacles in your mechanism that come from small divisors and resonances. So approximate solutions of your problem should not solve some Diophantine equations. And what you do to avoid these things is you have to be very careful in choosing which initial data survive. So which kind of tori survive. And actually in finite dimension, there is this very nice thing that a good way is that you parameterize the tori by the frequencies, and the tori which survive are the ones with Diophantine frequency. So there is, well, there are also the Diophantine tori surely survive. So there is a very straightforward path and well established to dealing with these things. And also, you know that in the complementary set, you can see chaotic behavior and the instability, which I mentioned before. So what happens in infinite dimension? Well, essentially, nobody really knows in the sense of before. You don't know what happens to typical solutions, whichever might be your meaning of typical, provided that it makes some sense. So you know that if the equation is integrable, well, this is, you know, typical solutions are on infinite tori, which is reasonable. They are the maximal tori. But when you add the perturbation, so when you get out of the integrable setting, essentially you don't know. There is no result on this type. What there is a wide literature of existence of finite dimensional invariant tori inside the infinite dimensional phase space, but these are absolutely not typical. And then there are some special results on finite dimensional, on infinite dimensional tori, but they're special and actually they're not very natural models. So there's lots of things to do. And also there are some examples of unstable orbits. So let me go through some literature. I lost track of how much time I have. 20 minutes? Something like that. Okay, so I should be fine. So first results were on simple model PDEs, and what actually, instead of working on a one-dimensional torus, so asking X is periodic, they asked Dirichlet boundary condition. And that introduced some simplifications. And so there were various very good people working on this and giving a lot of number of results. And the difference between this first two line of results and the second is that the first line of results used the Dirichlet boundary condition, but actually was able to prove linear stability around the tori, so a stronger result. While the approach by Grégoin and Bourgain proved existence, but not linear stability. And this actually appears also in higher dimensional models. So you see, if you look for a nonlinear Schrödinger on an n-dimensional torus, these results here, starting from Bourgain, end of the 90s, prove existence, but not linear stability. And to get linear stability of finite dimensional tori, you have to wait 12 years and some really new ideas. Then, well, there are also results or more general manifolds like spheres, or I mentioned compact Lie groups, where you can again prove the existence of quasi-periodic solutions. Then another class of equation on which there is still a lot of work going around is the case where the nonlinearity has derivatives, which I remind you it's more and more difficult the more derivatives you have in the nonlinearity. And here, well, again, I mentioned some names, but maybe what I would like to point out is that actually there was pretty recent advances in the field because people were able to deal with fully nonlinear PDEs. So as many derivatives in the nonlinearity as in the linear term, which means apart from the pleasure of being able to do that, that you're able to tackle more realistic models. For instance, the equations of water waves. And so there is this paper here, Balbi, Berti, House, Montalto, proved the existence of quasi-periodic solutions for the water waves. And there was a series of other works that brought to that. And so what is the big deal here? Well, the big deal, in my opinion, is that you would like to go to higher dimensions. All these examples here dealt with the equations in one spatial variable. And you would like to go to higher dimension, and there are some partial results, but still a lot to do about that. So, as I said, there are many relevant questions going around. What I'm going to do is I'm going to concentrate on three because they're the ones that I like best and I contributed to also a little bit. So the first thing that I want to concentrate on is the problem of resonances. So as I said, if you can move these lambda j's, or if they do not satisfy some Diophantine equation, I'm happy and the results are simpler. But usually all these lambda j's are rationally dependent in physically relevant models. Actually, they're integers. So of course, I mean, either you change the model or you have to deal with these resonances. And then the trick, as is true also in finite dimensional Hamiltonian system, is that you have to choose correctly the linear solution from which is your starting point for a KM algorithm. So you're looking for a true solution close to an approximate solution, and the approximate solution should be chosen wisely. So you have two ways of choosing wisely. One is that you can choose the Fourier support of the solution, which means that I'm taking a finite superposition of oscillations, and I get to choose which Fourier modes in the Fourier index z to the n I get to excite. So these should be chosen wisely, and wisely means in a generic way, and in a generic way it can have many meanings, but let's say that most choices should be good if you're in a big enough ball in Zn. And then once you have chosen the Fourier modes, you can choose the amplitude of oscillations of the linear solution. And this amplitude will be chosen in some rather complicated set, which will have positive measure in R to the D. And this is the kind of tip. So this is what you would like to do, and it becomes harder and harder in more complicated models. So another question, which I find extremely fascinating, even if you're wise enough and play the game that I explained with choosing a linear solution wisely, still you have a big problem coming from the fact that if you take a PDE and a compact manifold or n-dimensional torus, the linear eigenvalues will be multiple and with not uniformly bounded multiplicity. And that again is a serious difficulty in pulling through a KM algorithm. And the third difficulty is remember, derivatives in the nonlinearity. So these are the three things that I'm going to try to tackle, and I'm going to try to explain a couple of results, and then maybe give you an idea of how to deal with the resonance problem. So first result is on a one-dimensional nonlinear Schrödinger equation. So here the difficulty is the fact that I have as many derivatives in the nonlinear part as in the linear part. And just to make it in some way, I chose a nonlinearity where you see I have this second derivative here appearing in a degree higher than 1. So this is a 6-parameter family of equations. Now take any one of these equations. So sorry, these numbers should be all real. Now take any one of these equations and avoid This particularly degenerate case because it only has periodic solutions, unfortunately. Then here is this result on quasi-periodic solutions with Livia Corsi and Roberto Ferra. So this, it says, choose any generic choice of tangential sides, J1, JD. D is anything you want, but it's finite. In your Fourier mode set, which since we are in one dimension is Z. Now, I am looking for a quasi-periodic solution which is close to this linear solution here, which is supported on J1, JD. And how should I choose the amplitudes, Xc1, Xd? Remember, the amplitudes were the non-zero amplitudes of my linear solution. They should be chosen in some positive measure set, which looks like a set of satisfying Diophantine conditions. So it's very complicated too, but can be described explicitly. It should be in some small ball in the parameter space. Remember, these are D parameters. And what is nice is that not only it's a positive measure set, but the relative measure tends to 1 as epsilon tends to 0. And then the solutions that I find are both analytic and linearly stable. So this is the kind of result that I'm going to look at. And let me show you a version in higher dimension. So consider a nonlinear Schrödinger equation in dimension n. Okay, so I did not write this, but here I have n spatial variables. But no derivatives in the nonlinearity. Absolutely nobody is able to deal with derivatives in the nonlinearity. Now, again, you can produce a generic choice of tangential sides, J1, JD, in the Fourier space, which is Z to the n. And then you can find a quasi-periodic solution, which is a linear solution plus a small correction. And the linear solution is supported on J1, JD. And again, the actions, so Xc1, Xd, the amplitudes of the linear solutions, should live in a counter set, which is in a small ball in your parameter space. The only difference is that here, instead, the asymptotic measure goes to 1/2 instead of 1. But this is a rather technical reason that I will try to skip. And again, the solutions that I find are analytic and linearly stable. So this is a result with my father, Claudio Procesi, that's the second Procesi. And I must say that a similar result without the linear stability was also proved by Wei-Min Wang more or less at the same time. And let me try to give you an idea, because here the interesting point is what does it mean that the sites J1, J2, J3 are generic. So in my first example, it was really simple. But in the case in dimension higher than 1, well, it's a big pain in the neck. So it's generic, in fact, in the sense that they do not satisfy a certain explicit but extremely complicated polynomial. So in the algebraic geometry sense. But to produce this polynomial, well, it's extremely complicated. But here, I wanted to mention that the first result, in fact, was by Gangyu and Xu on the case n equal to 2. And then this genericity becomes, very much more simple to look at. And I wanted to show you because I find this very nice. So what is the point? You take your 3 points, which you want to say are generic. You take all the segments connecting the points, and you draw the line perpendicular to the segments, and you do it in all possible ways. Okay, now I drew just 2 segments. Then you go and look at the intersection points, which generically should be there. And you ask that these intersection points should not be integers. Okay, this is the condition that you want. You do it in all possible ways, and you do it also by drawing circles with diameters, 2 points. So you get a complicated structure, but you can prove that for most choices, in the sense most choices in a ball, of these red dots here, the intersection points are not integers. Remember that J1, J2, J3 should be integer valued vectors, of course, otherwise it's completely trivial. But the point is, what do you do in dimension higher than 2? This will never work. It's not possible because the lines here become planes, the circles become spheres, and the intersection of two planes would be a line which will always have integer points. So you had to give a completely different point of view. And maybe I will show you this point of view. I had to choose between showing this and giving a result on almost periodic solutions, but I think this is nice. So let me show you. What is the idea of genericity, which I'm drawing in dimension 2, but works in any dimension? So here, unfortunately, I had a picture with 4 points and I was too lazy to change the picture. So take these 4 points and you should draw, you should look at all, you see that these green dots form the 2 lines which are perpendicular to these 2 points. So you should construct all the sets of green dots which form a rectangle with 2 red dots. And they can do it in 2 ways. Either they are adjacent or they are opposite, okay? Now, maybe I should do this here because otherwise the audience. So draw a line, connect a graph, each 2 points that form a rectangle with 2 red points, okay? So I'm connecting, and of course I drew only very little lines. So generic means that I should ask, that I should be able to choose these points in order to make the connected components of this graph. You see that this graph, for instance, has a connected component of length 3. These connected components should be as small as possible. And in principle, it's not even clear that the connected components are finite in dimension bigger than 2, okay? So the theorem was rather complicated, so I want to study the connected component of the graph. And the theorem is that if you take 2 points that form, so the vertices of a connected component, it's formed by a finely independent points. So if you choose generic sets, each component has at most n+1 points. And this was really hard to prove in any dimension. I mean, this is where the collaboration with an algebraist came into play. And let me show you the picture. This means, look at these 4 points. These 4 points form a connected component. This would not be possible because 4 points cannot be finely independent in R2. Okay, so this is a non-generic configuration. Well, so this is nice, but what is the drawbacks of dealing with quasi-periodic solutions? Well, I think I told you they are not typical. And this is unavoidable. I mean, it's even non-typical in an integrable model. The other question is that all these solutions are very regular, which you might say it's nice. Well, okay, but in infinite dimension, you expect that even if you have a PDE with an analytic non-linearity, you would expect low regularity solutions. And with this mechanism, I am not able to produce them. And so, of course, you ask yourself, is it true that I have solutions which live on invariant tori and have a low regularity? But if you, or that are typical. Well, if you want to play this game, you must go to almost periodic solutions. So you must go to infinite tori. Well, as I said, there are very few results, most on cooked up models. And why do I say cooked up models? Well, first, most results are one-dimensional. But the bad thing, so I took a nonlinear Schrödinger example because it's the favorite example of everybody who tries for the first time to give these results. And the point is that if I want to prove even existence of almost periodic solutions, so infinite tori for this equation, I have to add this potential term, which is a convolution potential, meaning that, well, the usual definition of convolution, V star U is just the sum of Vj Uj, and the result will not hold for all values of this infinite list of parameters Vj, but they will hold for a positive measure set of the Vj's. So if you give me one equation and ask me, does this have an almost periodic torus? I don't know the answer, unluckily. But still it says that typical equations have some solutions. And then I think I don't have much time, so let me just show you some, let you read some names. So there are a number of results on almost periodic tori once you accept that you have to be able to move the equation a little bit. But unfortunately, they are either very regular, so they are few, absolutely not typical. They are either very regular solutions, or they may have, there is a result with a low regularity, but still very special. And so I wanted to show you, because I found the question of finding low regularity solutions that live in infinite tori rather fascinating. So I wanted to end by showing you a little bit this result, which has been in collaboration with Luca Biasco, Jessica Massetti, and that's all, sorry, and it's very recent. So if you look at this list of literature, you will see that here the regularity of the solution decreases, and here also the regularity of these parameters here decreases. And then you can read some names. So let me show you the result on low regularity solutions. So take your nonlinear Schrödinger equation with the external parameters. Now fix any number p larger than 1, okay? Now, for most choices of these parameters, remember that for me, the V are a list Vj, and for most choices of these parameters here in L infinity, so very low regularity potential, there exists infinitely many almost periodic solutions. And these infinitely many periodic solutions, I can find classical solutions, I can find regular solutions, but I can actually find solutions which I know are not classical, by which I mean they're not C2, they cannot be C2. And how do I know it? Well, these solutions look like this. They're a superposition of Fourier modes, and I know that uniformly in time, the supremum over J of Uj times, remember this is essentially mod of J to the P, is smaller than 1. And P, the only condition that I have is that P is larger than 1. So this has some regularity, this Fourier series, but the only thing that I know is that it has very low regularity. And actually, I know a bit more. I know this game like this. So these solutions, they are approximately supported on some sparse subset of the Fourier index set. Here I am in 1 dimension, so J lives in Z. So what does it mean? It means that I take a set with lots of holes. For instance, J is 2 to the H. And what I can tell you is that U hat J is actually bounded from below and from above by J to the minus P, but only on these red sets here, which means that the solution is actually very low regularity. So it cannot be a classical solution. But it also means that it's extremely special. So I don't know if I finished my time, but nobody says anything. So I go, no, because they were supposed to say something. So open problems, and then they will stop me. So open problems, there's many. Essentially, everything is open. First question is, could I play the game that I showed you before without asking that S has lots of holes? This would be really, really nice to do, but essentially there is no ideas about it, unfortunately, at least not that I have. And second question, okay, convolution potentials are ugly. Can I play the same game with a multiplicative potential? Still very hard, but more approachable. Essentially, it's a question of how well can you describe the spectrum of this Sur-Liouville operator here. So it's a nice question. Third, well, let's say I don't like potentials at all. Sorry. Can I play exactly the same game by modulating just one parameter? This equation here, this is a beam equation. It's much more natural than adding a parameter to me. So could one play with this game?
You're very close to the end.
Yes, and I'm also very close to the end of the slide. So, and the last question, again, a Graal for it is, it's no ideas. Could you say that something about typical solutions, at least typical in some possibly very strong regularity class. And I will end here because, of course, this is the nicest question. And thank you for your attention. So what happens now? Herbert? What is supposed to happen?
Dear Herbert, please unmute.
Okay. No, okay. Well, okay. So I was apparently unmuted. So, Andrea, Michela, I just want to sort of thank you for a very beautiful and interesting talk, and also in the name of those people who you cannot see. So thank you very much. I just want to clap and.
Thank you. Okay. So I guess it's finished the registration because